Today, we're diving into one of the most powerful and, frankly, world-changing stories in all of human history. How we figured out how to unlock the incredible power hidden inside the atom. It's a force that has literally shaped our modern world in two completely opposite ways, from the absolute terror of atomic warfare to the amazing, life-saving tools of modern medicine.
I know, that sounds like something straight out of science fiction, right? But this question gets right to the heart of our story, to this wild scientific truth called energy density. It's the mind-blowing idea that a colossal amount of power is locked away inside the tiniest bits of matter. And you know, the quest to unleash it didn't start with some big explosion, but with a really simple question. What exactly is an atom?
So here's a quick look at our journey today. We're going to start with the discovery of the atom's core and see how that discovery led to igniting the very first chain reaction. Then we'll uncover the world's biggest secret project, see how it totally changed warfare forever, and then pivot to how that exact same power is now used to heal people and explore the universe. And finally, we'll take a hard look at our nuclear legacy and what the future might hold.
All right, let's get into it. To really understand this, we have to rewind the clock a bit, back to a time when our picture of the universe was, well, a lot simpler. Before we could even think about harnessing the atom, we first had to figure out how to see inside of it.
You see, for a long time, scientists thought an atom was basically a tiny, solid billiard ball, the smallest possible thing you could have. But then, a guy named Ernest Rutherford did this brilliant experiment. He shot these tiny particles at a super thin sheet of gold foil. Now, most of them went right through as expected, but some of them bounced straight back. And that was staggering. It could only mean one thing. The atom was almost entirely empty space, with a tiny, unbelievably dense center, the nucleus. In a flash, the old billiard ball idea was shattered. The atom was really a miniature solar system. This analogy just nails it. Think about that for a second. If you scale an atom up to the size of a huge football stadium, the nucleus, the part with almost all the mass and all the power, is just a single marble sitting in the middle of the field. Everything else is just space. This discovery immediately brought up a brand new, very big question. What kind of incredible force could possibly be holding that tiny little marble together?
And here it is. This is the theoretical key that unlocked everything. Albert Einstein's famous equation. It's way more than just a cool formula. It's a recipe. It tells us that mass and energy are really just two sides of the same coin. The really important part is that c squared, the speed of light times itself. Because that number is just astronomically huge, the equation proves that if you could convert even a microscopic amount of mass, you would release a truly gigantic amount of energy.
So the theory was there. It was on paper. But how do you actually do it? How do you get that energy out of the nucleus when you want to? Well, that's where we move from pure physics to some serious engineering and the incredible discovery of the chain reaction.
This whole process is called fission, and it's basically the engine of the entire nuclear age. The best way to picture it is like a cascade of cosmic dominoes. You start things off by shooting one tiny neutron at a big, wobbly atom like uranium-235. That atom splits in two, releasing a burst of energy. But, and this is the critical part, step 3, it also spits out a few more neutrons. Those new neutrons then fly off and smash into other uranium atoms, which also split, releasing even more energy and even more neutrons, and on and on and on. It's a chain reaction that escalates in a fraction of a second.
And what's crazy is how fast all this happened. The idea went from just a concept in Leo Szilard's head in 1933 to something so real and so terrifying that he got Einstein to co-sign a letter warning the President of the United States about it. And then, just 3 years after that letter, a team led by Enrico Fermi in Chicago actually did it. In a secret lab, literally under a football stadium, they built this pile of uranium and graphite and created the world's very first controlled nuclear reaction. Humanity suddenly had a switch to turn atomic power on and off. Okay, so the science is proven. But now, World War II is raging, and the focus shifts dramatically. This isn't just about scientific curiosity anymore. It's about survival. And it kicked off what was probably the largest and definitely the most secret research project in all of history.
Just let that number sink in. 130,000 people. That's like the entire population of a decent-sized city, all secretly working on one project. And the wildest part? Most of them had absolutely no clue what they were actually building. They just knew that their little piece of the puzzle was vital for the war effort. The scale is just, it's hard to even wrap your head around.
And we're not just talking about a few labs here and there. The Manhattan Project built entire cities from scratch, in total secrecy. Places like Oak Ridge, Tennessee literally popped up out of nowhere, full of massive factories dedicated to enriching uranium. Meanwhile, out in the New Mexico desert, the Los Alamos lab became the scientific command center, where the smartest minds on the planet were tasked with actually designing the weapon. And the one thing driving all this secrecy, all this expense, it was fear. The terrifying fear that Hitler's scientists would get there first.
And that, of course, brings us to the first and most devastating use of this new power. The moment that secret was revealed to the world, it changed everything. It changed the very meaning of the word war. After the war, when the Soviet Union got their own bomb, the world entered this terrifying new era defined by a concept with a fittingly insane acronym, MAD, for Mutually Assured Destruction. The logic was as chilling as it was simple. The only thing stopping a nuclear war was the absolute certainty that if you launched your bombs, the enemy would launch theirs before yours even landed. Total annihilation was guaranteed, for both sides. It was a bizarre kind of peace, kept alive only by pure, unadulterated terror.
This analogy just makes the twisted logic of MAD crystal clear. For decades, the world's superpowers were locked in this tense standoff. The weapons they had built were so powerful that their only real purpose was to make sure they were never ever used. But hey, the story doesn't end in a mushroom cloud. After the war, scientists started to ask a different question. What if we could take this incredible power, and instead of using it to destroy, we used it to build? This was the beginning of the Atom for Peace era.
You see, a weapon and a power plant run on the exact same science, nuclear fission. The only difference, really, is speed. A bomb is an uncontrolled, all-at-once chain reaction. A power plant takes that very same reaction and slows it down, carefully controlling it to release heat steadily, which then boils water, creates steam, and generates electricity.
And the good it's done? It's pretty amazing. Nuclear power gives us a huge amount of reliable, carbon-free electricity, day and night. In medicine, nuclear tech lets us see inside the human body like never before. PET scans use radioactive tracers to hunt down cancer, and then targeted radiation beams can destroy it with incredible accuracy. And out in space, nuclear batteries are like tiny suns, powering missions like the Mars rovers and the Voyager probes, which are exploring the cold, dark depths of our solar system, where solar panels would be totally useless.
Which brings us to today. We've inherited this incredible, but also incredibly dangerous technology. The challenge for us now is to manage all the risks that come with it while still trying to harness its amazing benefits.
Of course, we can't talk about this without talking about the catastrophic failures. Chernobyl was a perfect storm of a deeply flawed Soviet design and terrible human error. The big lesson the world learned from that was that safety can't just be an add-on, it has to be built into the fundamental physics of the reactor itself. Now, Fukushima was different. That was a modern, safe reactor hit by a natural disaster that was literally beyond anyone's imagination. The lesson there was about having ultra-robust, redundant backup systems that can survive even the unthinkable. Both of these terrible events forced massive improvements in global safety standards.
So what's next? Well, all the nuclear power we have now comes from fission. That's splitting heavy atoms apart. But the holy grail, the real future, is fusion. That's smashing light atoms together, the same process that powers the sun. The promise is almost too good to be true. A nearly limitless fuel source from seawater, basically no long-term radioactive waste, and it's physically impossible for it to have a runaway reaction. The catch? Well, we have to create and somehow contain temperatures that are hotter than the core of the sun. It is, without a doubt, one of the greatest engineering challenges humanity has ever taken on.
So this is where we end up. It all started with a simple question about what matter is made of, and it led to a power that has completely defined the modern world. It offers us the dream of a clean energy future and the tools to explore the cosmos. At the same time, it carries the heavy burden of our most destructive invention. The science is in our hands now, and the choice of what we do with it, well, that remains the defining question of our time.